We're going to talk about the derivative of a vector in a rotating frame. I draw your attention to this beautifully drawn figure here. Its salient points, salient features are that there is a fixed coordinate system, O, big X, big Y, and associated unit vectors, cap I hat and cap J hat. That's the world from which the vantage point from which we observe this whole thing. Then there is a rotating frame, and this rotating frame is labeled A, little x, little y. It deliberately has its origin superimposed on the other, but you'll see why momentarily. And this rotating frame, this frame is rotating with an angular velocity, omega, and an angular acceleration, alpha. These are both defined as positive in the counterclockwise direction. Right-hand rule applies. And now this is the kind of key point where the rubber's starting to meet the road. The vector, we have presumed the existence of a vector. We're interested in it. We're going to call it RAB because it goes from A to B, but as far as this discussion is concerned, it's simply a vector, all righty? The key point is that this vector is defined in this rotating frame, this little x, the little y frame. Fair enough. So, if I may bring this down, I guess. Play a little board games here. Okay. So here is that statement right there. I'm going to do this. I'm going to say that R is defined by its component little x and little y are its components in the little I hat and little j hat direction. Everybody appreciate that? That's nothing more than the analog of those dotted lines there. All right, now we come along here and differentiate it. I want to differentiate this. Excuse me. Leaving nothing for chance here. To get the velocity of that point, and you get this. You simply use the product rule, and it is just as you would expect. Okay, everybody see that? Nothing magic here, never did my fingers leave my hands, nothing special happened. We simply took this expression and we differentiated it, okay? Each one. X dot I plus X di dt, or d dt I hat, Y dot j, Y d dt of j dot. All right. This raises a question, or you should be asking yourself, or excuse me, not that. What the heck is this? All right, the rest of it's clear enough, but what's that? How about, is it, I'm sorry, your name again is Nassum? Nassum. What are those two there? And why are they there? That's exactly right. The little I hat and little j hat are the unit vectors of the frame that's rotating, okay? The frame that's moving. And because it's rotating, they are changing in time. They actually have a derivative. Oh, hang on a second. This is great. It's like my own little Tetris game or something. if you examine this little figure here, you ought to be able to convince yourself that this is true. Okay, that is to say, if little I hat and little j hat are rotating, are changing with time, then their derivatives are here and here, respectively. And because they are unit vectors, their magnitude is unity, what is the rate at which they're rotating? The rate at which they're rotating is simply omega. All righty? So the magnitude of this vector and this vector are just given by these two expressions. Di dt, or dt of I hat is got magnitude omega, and it's in the direction of j hat. Similarly, d dt of j hat has a magnitude of omega, and it is in the direction of minus I hat. So, I can bring this down now. All righty. Let me rearrange this. Okay, let me just make sure I got that right. Yes, very good. Okay, now can everybody see that this expression is nothing more than a rearrangement of the one above? Okay, it's simply, we had here the product rule, and all we're doing is organizing these two, putting these two terms first and these two terms second. And then when we put this in here, okay, well, let's see if we can get this, send them both out of town here. All right, now, then we have simply plugging those in. And this is the point, all right, that these first two terms, these two guys right here, oh, sorry. Okay, are simply that, omega cross r. Now, the second two, the other two, your book calls okay, it's called that. Let me bring this down here. Okay, so let me go straight to the punchline. This is one to remember. All right, the velocity of r, that is that vector's time derivative in that rotating, the vector in that rotating frame's time derivative is omega cross r plus v rel. Did everybody read that? Can you guys in the back see that? All righty. Now, this, let me just kind of sort this out for you here. This first term whereas the second here okay, this second term, yes, sir.
David, Mike help with the R you're talking about.
Oh, that is, I'm sorry, that is absolutely correct. Thank you. Up as well, thank you. Absolutely right. All right. Okay, so this is what we're after. Conceptually, what we're talking about is that this isn't just an I mean, it is an expression. I mean, it's just an algebraic expression, but it has meaning, all right? This is the velocity of that point as seen from the ground. That's basically it. And it basically says when I watch that thing running around, when I watch that point move, what I see consists of two parts. One, a part that flows from the fact that the frame is rotating, and the other flows from the fact that the point is moving within the frame. Clear enough? Okay, let me, in the interest of time, simply, here's a kind of major takeaway that we can kind of generalize this to any vector, not just that point, not just a position, but any vector in a rotating frame. Derivative can be taken by taking its time derivative, that's to say its velocity in the frame plus omega across the cross product. All righty? Questions, comments? Everybody with me? Yeah, your name, please. Ronald.
So is this within, like, is DAB, are we writing an equation for, like, looking at it within the rotating frame, or are we looking at it from the fixed coordinate system?
Your name again?
Ronald?
Ron, I'm listening to the question here. Ronald's question was, what is it that's being talked about here? What is this animal right here? Answer is, this is the velocity, in the conventional sense, the velocity of that point B as seen from the ground. So it's the velocity of that point in the fixed coordinate system, having had itself expressed in terms of the rotating frame. All right, so if somebody tells you, I know where a point is in this rotating frame, and I know that the frame's rotating, you can go, whoosh, tells you where the point, what the point's velocity is with regard to the fixed, with respect to the fixed coordinate system. Make sense?